Let's prove this formula holds using mathematical induction. So once again, we're going to use our first principle of finite induction here, where we check our base case, which is the lowest integer we're interested in. Here it's n equals 1, and then we'll assume the formula holds for a value k, and use that assumption to prove it holds for the value k plus 1. So first off, for the base case here, the lowest integer we're interested in is 1, so we'll plug in 1 into our formula and see just directly that this formula does hold for n equals 1. From there, we can move on to the inductive step. So for the inductive step, we're going to assume what's in white here, which is the formula holds for some value k. K represents a positive integer, and we're going to use that to show that the formula holds for the value k plus 1. And so whenever it holds for k, it holds for the next guy. Because we already checked n equals 1, this means this formula will hold for all positive integers k, or for all n greater than or equal to 1. So before we get started, I can make a couple simplifications here. I already plugged in k plus 1 into green, but I can essentially combine my 2's and 1's there on both sides to give me this formula here. Now, I could also continue to FOIL this out on the right and possibly on the left expand those 2k minus 1 squared. Typically, we don't do that, though. Typically, we keep whatever patterns or products we can here, because that's really what we're trying to show is this formula. And this formula, for example, has a 2n minus 1, 2n times 2n plus 1 kind of shape to it. So we typically keep that. So the rest of our problem is to take what's in white and use that to prove what's in green. A very common approach is to look at the left-hand side of what's in white and just add in what we're missing. So because in order to create the green formula, we have an extra term on the left-hand side of the green. Let's just add that term on both sides of the white. Now I'm trying to make the white look like the green. The left-hand side, it's good to go. It is exactly what I want. The rest of this problem is about manipulating the right-hand side of the white so that it looks like the right-hand side of the green. First thing I notice is I need to make this a common fraction. So the right-hand side of the green is 1 fraction divided by 3. And so I'm going to make the right-hand side of the white into 1 fraction also divided by 3. Now from here, what should I do next? It's not really clear. I can, expand out 2k plus 1 squared. But first what I'm going to do is I'm always looking at the right-hand side of the green. I'm looking for k plus 1 times 2k plus 1 times 2k plus 3. Can I factor out one of those terms from what's in white already in the numerator? And indeed, I see I can actually factor out 2k plus 1. And so it makes more sense right now to factor out 2k plus 1 than it would to expand that 2k plus 1 squared term that we saw. And then from here, it's, hey, I already got the 2k plus 1. Where am I going to find k plus 1 times 2k plus 3? Well, now we can combine like terms. And if you remember how to factor out quadratics here, you'll start to see that indeed this 2k squared plus 5k plus 3 can be factored out into what we want, and then we can rearrange terms and we're finished with the problem. Now, what if we don't remember how to factor 2k squared plus 5k plus 3? Well, because we already have what's in green, we know where we're going. That's what kind of helps us along here. And so I want this equation to be true. I want 2k squared plus 5k plus 3 to be true, to equal 2k plus 3 times k plus 1. And so you can actually just kind of start with the answer there and make sure that the equation's true, and it does, and you have a nice little workaround. Make sure to like and subscribe and let me know what you want to learn next.